colligative properties are properties that are dependent on the concentration of a substance. So if you have a higher concentration, you would have a different property than if you have a lower concentration. The picture that's shown here is up to 7 different moles diving into a beaker of solution. So the colligative properties would change depending on how many of the moles were dissolved in the solution. The 4 colligative properties are vapor pressure, freezing point depression, boiling point elevation, and osmotic pressure. There is another factor to consider along with concentration, and it is whether you have ions or substances that do not dissolve that are called non-electrolytes. In the case of colligative properties, it matters how many ions you have dissolved or how many particles are dissolved, because the number of particles will change the overall effect. So if you are dealing with substances that are ionic, for instance, K3PO4, when you dissolve a K3PO4 into water, you get K ions and a phosphate ion in your beaker. So as you can see that dissolving one K3PO4 will yield you 4 different things in your solution. So it matters that K3PO4 is ionic, and it, when dissolved, yields 3 or 4 different ions. If you have a beaker and you are dissolving sugar, for instance, so let's go with glucose, C6H12O6. Glucose is non-electrolyte, meaning it is not ionic, and it dissolves. It does not dissolve into ions. So when you put sugar or glucose into the water, you're going to have a C6H12O6 molecule floating around. And it has a factor of 1 versus K3PO4, which has a factor of 4. So when you're doing the Van Hoff factor, you need to decide if it's ionic, and if it is ionic, how many ions are broken up whenever you dissolve. If it's not ionic and it's a covalent compound, a molecule, then you don't have a factor to deal with. All right, our first colligative property is vapor pressure lowering. And by knowing what it's telling you, that will help you decide if you're doing the right thing. So what it's saying in this cartoon, it says, calm down and stop trying to evaporate. And you have your non-volatile solutes, and this poor little blue molecule over here says, yes, sir. The non-volatile solutes will lower your vapor pressure. So the equation that you're going to need to remember for vapor pressure lowering is P equals X times P naught. So the P is the vapor pressure. The X is the mole fraction. Here's your concentration. And your P naught is the pure vapor pressure. So you will need to look up the pure vapor pressure and calculate the mole fraction, and that will tell you what your new vapor pressure is. And these all have a factor here of I, because it's telling you that it needs to be for the same substance. So if you are considering water, then you would need the mole fraction of water, the pure vapor pressure of the water, to find the new vapor pressure of the water. So you need to have consistency among your terms. Freezing point depression being the key term here, freezing point depression will help you lower your freezing point by adding a salt. And if you look at the cartoon, it says friends keep you from freezing because they're all around this particular molecule, and they will help lower the freezing point. You see this in action whenever we salt the roads in the winter, and it's not necessarily for traction, but it will cause the ice to have, or the water to have, a lower freezing point, meaning the ice won't form quite as at the normal temperature. It has to be colder for ice to form on the roads. So the equation that you need to know is delta T equals K sub F times molality. Okay, now the delta T is a change in temperature. So remember, we're doing the final minus the initial for the temperatures. And that is equal to K, which is a constant. And then the molality is the moles per kilogram of the solute. So you would look up your K value in the constant chart, and they might give you the molality, and you would solve for either the change in temperature, or they might ask you to then calculate what the new freezing point is, because you would probably know the initial regular freezing point. You need to consider the Van Hoff factors in freezing point depressions. So when you are solving this, this is like if you have NaCl, remember that it's two particles, so you would need to double your factor. Boiling point elevation is telling you which way that the temperature change is going. And the cartoon says, friends, keep you cool. These guys make it harder for me to reach my boiling point. And the equation here is the change in temperature equals the K factor, or the K constant, times the molality again. And the K is a constant, which will be listed for you or given in the text. And you are then going to either find perhaps the change in temperature, or if you know what the normal boiling point is, you can subtract or add, you can add the original temperature to the change value, and that will tell you what the new boiling point is. If you add salt to pasta, you are in fact raising the boiling point slightly, but another reason that they add salt to pasta is to flavor the pasta. So there's two factors going on there. For boiling point elevation, you also need to consider the Van Hoff factor. And remember, like I said, NaCl, well, we know that it's two pieces, so we need to consider that when we're doing these problems. Osmotic pressure is the passage of a substance through a membrane or a particle. So most often we think of it as water, and you can see the cartoon here. They show you the water going into or out of the pig, and it exerts a pressure on that membrane. So osmotic pressure is the capital P or pi here. So that's osmotic pressure. And it would be measured in regular pressure units. The M is molarity. The R is our gas law constant, and we're going to use 8.314. And then T is temperature in Kelvin. So you would be plugging in various numbers and solving for either the osmotic pressure or the molarity. And you would see units of pressure like this 8.314 is in kPa. So typically we're going to see kPa as our unit.